All right, so we'll just begin. Yeah, so today I want to talk about, tell you about the what's called the deconfined quantum critical point. It's kind of a paradigmatic example of exotic quantum criticalities that appears reasonably naturally in condensed matter system. Actually, we have now quite a few microscopic settings where this kind of thing can arise, and it's also cases where the phase transition is naturally described by some critical gauge theory, well, or at least critical-ish. So, so let me tell you the most canonical microscopic setting where most of the time people talk about this setting. So it's in terms of quantum magnet. So think about a 2D lattice, the simplest one being the square lattice, where I put some spin 1/2 moment on each unit side, right? So on each unit side, I can have some spin moment, so spin 1/2 magnetic moment. And once you do that, you can ask, well, what is your ground state? Well, there are two very simple symmetry breaking ground state. One is the nail antiferromagnet, where you just align spin like up, down, up, down. This is what happens, for example, in cuprate. And so it's a state that breaks the spin rotation symmetry. Okay. This will be what you get, for example, if you have nearest neighbor Heisenberg interaction, antiferromagnetic Heisenberg interaction. Just ferromagnets are less interesting. There's no. Oh, ferromagnets tend to have less quantum fluctuation. Just have all spins pointing one way, and then it's an exact ground state. That's not a super intrinsic reason. In fact, there are examples where ferromagnet can give you something like that, but it's just less common. Right? Let me put it that way. Yeah. So, because if you think about quantum spins, antiferromagnetic interaction naturally gives you quite a bit of fluctuation already. You can already see that this kind of classical pattern is not actually the exact ground state of this Hamiltonian. While for ferromagnet, Sorry?
I don't see this.
Oh, yeah. You just take, yeah, this is a classic exercise. Just take two spins with the Heisenberg interaction. If you have ferro interaction, then just, all spins aligning the same direction is an eigenstate. But if you have anti-ferro, the ground state is a singlet, meaning the ground state will be up, down, minus down, up. So any classical picture in which the spin just pointing in some direction and not moving is not an eigenstate. It's not your ground state. So it's actually quite a bit non-trivial fact that when you put an entire lattice of such spins together with the nearest neighbor Heisenberg, this kind of classical pattern more or less is your ground state. I mean, historically, that actually caused a lot of debate, let's say, between Nail and Landau, for exactly that reason. But we now know that, at least on the square lattice, even with this interaction, this is eventually the good ground state. Yeah. So, but even this simple argument, you can see that antiferromagnetic is kind of the good starting place if you want quantum fluctuation to give you something interesting. So this is one well-known ground state. The other one, you can get, for example, by adding on top of this some other more complicated interaction, ones which Anders played around a lot, with some more further higher, multi-spin couplings, is called a valence bond solid. So that's a state. So this is a spin singlet state. So in In terms of picture, it looks like this. So I'll explain the notation. So each of this ellipse is actually just this. It's just up, down, minus, down, up. So it's a spin singlet. Since this is a spin singlet, by definition, it does not break the spin rotation symmetry. However, just by looking at this pattern, it's obvious that it breaks some lattice symmetries quite badly. For example, if I think about a 90-degree rotation around a lattice point, this nail pattern does not break that. It's still 90-degree rotation symmetric, but this pattern is not. Okay, sorry. So this magnetic state is sometimes called nail or collinear antiferromagnet. I'll just call it antiferromagnet or sometimes nail. So this is VBS. It's sometimes also called dimer order. Okay. So the funny thing that could happen is that if I imagine tuning some microscopic order parameter, let me call it R, there could be a continuous transition. Or in principle, there could be a continuous transition between the two, or continuous-ish. The reason why people got excited about the possibility of such a transition is that this transition is intrinsically non-lambda. That's because you cannot describe this transition with a single condensate of a local order parameter. Because if you do that within Landau theory, that requires the unbroken symmetry in one of the faces to be the subgroup of the other. Right? But you don't have such a structure here. Here you have the 90-degree rotation, but not spin rotation. Here you have the spin rotation, but not the 90-degree rotation. So they are not subgroup of each other. And that fact alone forbids you from writing down an unfine-tuned single direct continuous transition within Landau theory. So that's the setup. So now let's construct a field theory for that for this one. Right, right, so we know what it is not, right? But still, let's think in terms of order parameter for a little while, right? In particular, it turns out to be quite convenient to start from the valence bond solid phase, and think about the order parameter there. So let's think about the VBS order parameter. So as I said, it breaks the lattice 90-degree or C4 rotation symmetry. So naturally, it's an order parameter that transforms non-trivially under Z4. But if you are familiar with things like Wilson-Fisher type of phase transition, Z4 is not very different from U1. In particular, I can think about a complex scalar. Let me call it phi. And under the Z4, I pick up a phase factor pi over 2. Right? That's, you can write down the real imaginary component, make it two-component real scalar. It doesn't really matter. Okay, so this Z4 is pi over 2 lattice rotation. So if you did the Landau theory, which we know is incorrect, but if you did it anyway, so if you do Landau theory, then the transition from a phase where this Z4 is broken, like the VBS, to a symmetric phase will be described just by the Wilson-Fisher sorry. Yeah. It's the 90-degree lattice rotation. Let's say you take that. Yeah. So if you do Landau theory, we know it will not work. You know, Landau theory means Wilson-Fisher in phi, because the disordered phase will not have the Néel antiferromagnetic order.
Can you write the full Lagrangian? Because how do you implement this Z4 break? Right? So you are thinking in terms of the Wilson-Fisher O2?
Yeah. I'm thinking in terms of the Wilson-Fisher. I'll write down the Lagrangian very soon. Yeah. Okay. Actually, let me just write down the Lagrangian, because I'll use that anyway. So suppose I think in terms of the Landau way, I'll have this. Sorry. It's complex square phi 4. Importantly, I don't have the full U1 symmetry. I only have Z4, which means I should have an anisotropy, a fourfold anisotropy added. Okay, and RC is, as usual, tuned to the critical point. I'll come back to that soon. But the important thing here I want to emphasize is that it won't work because the disordered phase where your phi do not condense looks trivial. It doesn't have anything that looks like antiferromagnetic order. Has no AF order. Yes? Yes?
The valence bond solid also breaks the translation.
Yes, it does.
So,
yeah, it turns out you'll do similar things. I think I chose not to focus on translation because it simplifies the story, but you can certainly do it. For example, I think under TX, depending on exactly how you do it, it's something like this, and under TY, I think it's minus. It's either minus or with an I. I think it's a minus. So there's some specific way over it. Yeah. So it's not going to work, but let's do it anyway. See exactly where the things go wrong, right? So if I do Wilson-Fisher, this would be the action I write down, and this anisotropy, this fourfold anisotropy, is known to be irrelevant at the critical point, at the O2 Wilson-Fisher critical point. I think the support, there was some fairly old Monte Carlo data that indicates that it's irrelevant. Okay. So which means if I do that, then it's just the O2 Wilson-Fisher, which we spent a lot of time talking about over the past several days. In particular, you can go to the vortex picture. You can apply this boson vortex duality to just formulate that as a bosonic QED or Higgs transition. Again, with some fine-tuned mass, with the Maxwell term, right? Old story. But suppose we also want to translate this into the abelian Higgs side. Well, as we talked about before, the phi boson, the charged boson in the gauge theory becomes the monopole, the operator that flips the gauge flux by 2 pi. So phi to the fourth is just a fourfold monopole, like, it flips your gauge charge by 8 pi. So essentially what you get is a fourfold monopole. And again, this is irrelevant. But let's just keep it there in case we need it. Okay. So this would be what it looks like in the vortex picture. Now we can ask what is going on? What is wrong with this picture? 2 plus 1, sorry, the lattice is 2-dimensional. Yeah. So what's wrong with this? Why don't we get the right disordered phase, right? Well, the thing is, if you actually look at the valence-bound solid order, the vortex has structures that's not captured in this abelian Higgs theory. So, to show that, let me literally draw a vortex for you. Okay, it's a Z4 order parameter, so a vortex is really the crossing point of two domain walls. You can actually draw it. Let me draw it. So this will be worth it. So, but it takes some time to draw it right. So let me say I have this kind of valence-bound solid pattern. But starting from here, I want to rotate it 90 degrees. So instead, I have like this. Right. So and then in the upper right corner, it's all aligned like this. But then, starting from here, I decide to rotate it again by 90 degrees. What do I get? I get this. Okay. Sorry? Yes, because I want this pattern to be this pattern rotated by 180. If I do this, you find that it's actually the same pattern. So this pattern rotated by 180 is not the same as itself.
It depends on you rotate with respect to the point of the size of the lattice or the bond midpoint or
Yeah. So I'm rotating around along a point where the symmetry is actually broken. Right. So yeah. So essentially there are 4 inequivalent configurations, and I'm trying to put these 4 inequivalent configurations into this domain wall structure. Hopefully it will become clearer after I complete the picture. So let me just do it. So now, sorry, let me not. And then on this side, I decide to further rotate this guy by 90 degrees. I get this pattern. Actually, as Slava just pointed out, when I draw it this way, there's this poor guy that's left over, not paired to. Anyway. No, that will not count as a domain wall, though. For example, if I do this, then it's not a domain wall, right? Because I'm just it doesn't look very different from that pattern, right? So I do want to create domain walls where that pattern changes. Now, the thing is, if you move it this way, in some sense, you're just moving this unpaired guy, pushing this unpaired guy to the right.
Can I just
Okay, sure.
This is training week. I could do myself like this.
Yeah.
Then this. Then this. And then this.
Yeah, that's the. So, yeah, the thing is, if you think about what a vortex does, right? If you really think about a Z4 clock-like order parameter, to get a vortex, you want something like this. You want it to rotate. This is the anisotropic version of this continuous rotation. But if you do it like what you draw, it's more like this. This is like you're doing halfway, but then you're rotating back. Sorry, you're like this, but then you're rotating back. So that's not a vortex, right? So essentially, yeah, think of it first as a continuous variable, and then let's worry about anisotropy later, right? Once you think about it that way, you prefer to call it a vortex, you prefer this.
In your construction, my construction is that you rotate around the side, and I can rotate around the midpoint of the plaquette.
Okay.
So why is yours
Okay. Let me do it more carefully. Yeah, I can. No. Here's how you do it. The statement is that they are. Oh. Okay. Yeah.
The point is that the phase in the lower bottom can be obtained from the phase in the upper left by the continuous shift by finite number.
Yeah. Yeah. So the important thing is, as long as we call it a vortex, at least something that mimics the vortex here. The non-trivial thing is, doesn't matter how you draw it, there will be this poor guy, a single spin, unpaired left. Single, unpaired. I think these two words are redundant, but anyway. An important thing is it's a spin half moment. Right, so the statement is your vortex transforms as a spin half object under the global SO3 rotation. And of course, in the Billian-Higgs theory, that feature is not there. There's no SO3. So what do? What's the minimum modification of the vortex Billian-Higgs theory to accommodate this feature? Well, you do something that almost sounds trivial. You replace this phi tilde, that Higgs field, by a two-component phi tilde that transforms as a or let me just say SO3 spin half. Right. So you replace phi tilde by phi tilde up and phi tilde down. And now let me change notation a little bit. Let me instead of calling this phi tilde, let me just call it Z alpha. It's just a name change. And then write down the theory. So it's a U1 gauge theory, but now coupled to a two-component two-component complex scalar. Again, with a fine-tuned mass term. And a quadratic term. And again, the monopole, fourfold monopole provision. So this is sometimes known as the Cp1 model. Because if you look at this Z, it's a two-component complex fermion, but with the common U1 gauged. So that's Cp1. But the thing is, okay, sorry. Let me just comment first that it turns out to be still true that this fourfold monopole is still irrelevant. It's not obvious from the outset, but it turns out to be, from all the evidence we have, it's irrelevant. So then you have the Cp1 model. If we throw that away, without monopole perturbation. So the statement, having no monopole perturbation just means this topological current, which is the star dA over 2 pi, we've seen many times before is now conserved. Okay. So this is.
So index alpha runs from 1 to 3.
Sorry, alpha is 1 and 2. It's just spin up and spin down. It's a,
Okay.
yeah. So in the literature, this is sometimes called, somewhat confusingly, non-compact Cp1, or just NC-Cp1. So non-compact is just a shorthand way to say you don't have monopole perturbation. It's not really saying your gauge group is non-compact. I mean, gauge group is always U1. So, okay. So this is the theory. The field. This turns out basically to work. This is the field theory describing the Snell VBS transition. Okay. Yes. Yeah. I'm going to show you now. Yeah. I'm going to check the phase diagram for you, as I always do. It's pretty much always the only thing I can do. So. So now let's check the phase diagram. There's a mass which I tune to critical point, but then let's tune away. Let's add the mass. Let's put the mass perturbation back. So if mass is greater than 0, then this charged bosons are just gapped, so just throw them away. What do you have left? Well, you're left with then a pure Maxwell theory. But now with multiple perturbation, let's put them back. So you have Maxwell plus monopoles. If you don't have monopole, it's just free photon, and it's effectively superfluid, nothing too interesting. But now this monopole guys becomes relevant. And leads to confinement of the U1 gauge theory. This is the famous Polyakov mechanism. In fact, to see that this monopole leads to confinement, or leads to leads to a gap of this U1 gauge field, you don't need fancy arguments from Polyakov. You really just notice that, remember, as I emphasized, in 3D, a U1 photon theory is just a superfluid or a Goldstone boson written in a different basis. So this theory in 3D is basically just, it's just a Goldstone mode of a superfluid, of a spontaneously broken U1 symmetry. And in this language, this monopole operator, this fourfold monopole operator is basically a cosine 4 theta perturbation. Right? Unlike in 2D, where for a free compact boson, this cosine has some algebraic correlation function, in 3D, this is just a constant correlation function. So once you add it, the Goldstone mode becomes unstable. It gets a gap. That's the so essentially this behaves like a mass term. So this leads to a gap. And furthermore, the cosine 4 theta will prefer the theta to order. Yes?
I'm just kind of confused how we got to this Maxwell theory.
Yes.
The first
Yeah. I'm now in this regime. So the Z boson's got a mass. So let's go to, make this mass large and go to the energy regime below the mass gap, and then we just throw them away. I mean, integrating them out don't give me anything non-trivial. Yeah. Oh yeah. Sorry. Yeah. Yeah. So in general, they're there. Yes.
No, I think the original Wilson-Fisher theory with spins to be the old this.
Sorry.
The theory that I started from, that we initially, gauged, right? Can I take that and put a spin on it and let it solve to this theory?
Oh, you mean the ungauged Wilson-Fisher? Yeah, that would be a totally different thing, right? Because there, you're kind of describing something that looks like a magnet, but the problem is the disordered side is not a VBS, right? And then